Good afternoon. This is Professor David J. De Los Reyes. Okay, I got a new topic this afternoon on my channel. Okay, let's proceed. My topic this afternoon will be lesson number 100. We are now on lesson number 100 on my channel on the topic integral calculus, subtopic surface of revolution. And the discussion for this afternoon will be Frustum of a right circular cone. We will derive the total surface area, lateral surface area, of a right circular Frustum of a right circular cone if the lower radius is big R, upper radius is small r, and the altitude is h. Using another solution. Yesterday, we derived but the total surface area because we integrate with respect to y. For this afternoon, we will integrate with respect to x. So actually, lesson number 99 and 100 are similar, except that lesson number 99 is actually the solution if we try to integrate with respect to y, and for this afternoon, we will integrate with respect to x, and supposed to be the lateral surface area going around should be the same. Okay, I will try to read the problem. Derive by integration the surface area of the frustum of a right circular cone by using differential x. Yesterday, we integrate with respect to y. Okay, for today, we will integrate with respect to x. So actually, the figure will still be the same. The right triangles will still be the same. The relations will still be the same, but I will try to explain the relation, okay? I will take tangent of theta. From the frustum of the right circular cone, actually we could bring out two right triangles. The first right triangle is this one, the bigger one. The smaller one is this one. So if I will try to expand this to here, I will place it here. This is the bigger right triangle. This is the smaller right triangle. This point here is actually a point on the slanting of the frustum. The coordinates is actually xy. Meaning, this is x and this is y. So actually, we are considering the equation of the slanting. Okay, we'll take tangent of theta. Horizontal line, theta is theta. So using the bigger right triangle, tangent of theta will be this side here, all over the total side. It should be x over big R minus small r, equal to, take the tangent of theta using the smaller right triangle, it should be this side here, all over this. It should be y over r minus x. It should be y over r minus x. If we try to compute for y, y will be the ratio h over big R minus small r times the quantity big R minus x. Solving for dy dx. We are trying to bring out the solution, and the integration should be with respect to dx. So it's a must that we will take the differential y with respect to x. So what will come out on the right hand side will be a dx. Taking the differential, dy dx will be equal to h over big R minus small r. The differential of this will be 0 times minus 1. R is constant, differential will be 0. Minus x, we are taking the differential or derivative with respect to x. So this is times minus 1. The derivative of x with respect to itself is negative 1. So dy dx is actually, I will try to rewrite or reorient the arrangement. It will be negative 1 because this is negative 1. Negative 1 times h over the difference big R minus small r. Squaring both sides, dy dx quantity square equal to negative 1 square, it will become plus now. H square will be h square, and r minus r will be big R minus small r counted square, equation number 1. Solving for the length of the differential arc. Differential arc is equal to the square root of 1 plus dy dx quantity square times dx. Okay, this should be dx because the problem is asking that our solution will be integrated with respect to x. So if we try to substitute now, ds will be 1 plus the square of the first derivative is actually h square over r minus r quantity square times dx. Okay, we cross multiply this one, so this will go up. So what comes out will be h square plus this difference of the square of this. The bottom portion will be the square root of r minus r quantity square. It's a perfect square, so I took the square root. What will come out will be 1 over r minus r without the radical sign times the square root of h square r minus r quantity square times dx, equation number 2. Okay, let's try to bring out the total surface area rotated with respect to the y-axis. The total differential area of the frustum rotated with respect to the y-axis. That's the significance of this subscript here. It should be 2 pi times radius times ds. But the radius of the differential area is actually x. This is x. So this radius is x. So if we try to substitute now, differential s with the subscript y equal to 2 pi times x times dx, 1 over r minus r, times this radical sign here times dx. Oh, I just place this one. Substitute this one. Okay. So we try to rearrange. This r constant, 1 over r minus r is constant, 2 pi is constant, so we try to compress them into 1. So this should be 2 pi over the difference of r minus r times this radical sign here times x dx times x dx. Taking the differential now, the requirement of the problem is that we must have to integrate with respect to x, okay? We got the equation already. The integral of the total differential sy equal to 2 pi, I just rewrite this one. The integral of x dx, it's an easy money, guys. Okay, let's bring out the lower limit. The lower limit is small r, and the upper limit will be equal to big R. Let's go back to the figure. To cover up the total surface around, dx should move from R to big R. Or it could be from 0 to R, then from R to big R. Or in short, it will be from small r to big R. This is small r. This is here. And this is big R. So this is our lower limit, and this is upper limit. Okay. So the limits of the integration will be from small r to big R. I will rewrite this one. These are all constants. The integral of x dx, it's a power formula. It will be x squared over 2 with the limit from small r to big R. I will rewrite this one. Okay. Substituting the upper limit will be big R squared over 2 minus small r squared over 2. And if we try to simplify, I will rewrite this one, and actually this is 2 and 2, so actually we could compress it into one fraction. It will be r square, okay, hold on, r square minus r square over 2. But big R square minus small r square is r plus r times the quantity r minus r over 2. So the simplification of this will be r plus r times the quantity r minus r over 2. These two here cancels. R minus r cancel with this. So what will remain will be, this is r, guys. Okay. What will remain will be pi times the sum of big R plus small r times the square root of h square plus the difference of big R minus small r quantity square under one radical side. This is the formula. And if we try to inspect this one, it was actually the same as the formula using the integration with respect to y. It is this. This is the solution using the integration with respect to x, and this is the solution using the integration with respect to y. Okay, that's the second solution. Okay, so it's very interesting. One problem, we bring out two solutions, and supposed to be the resulting total surface area will be the same. I will repeat it for the last time before we go this afternoon. Pi times the sum of big R plus small r times the square root of h square, the difference of big R minus small r quantity square. Actually, the one under the radical height is this land height. Okay? It's the same. Pi R plus R times the given radical. Good afternoon, Los Angeles.